Welcome to the webinar, Identifying Future Platform Materials to Drive Industrial Innovations. My name is Tiffany Hua, analyst here at Lux Research, and I will be moderating today's session. Presenting today is my colleague, Kristen Marshall, Associate Research Director, also here at Lux Research. Throughout today's webinar, you can type any questions you have in the questions box on your screen. Time permitting, we will answer all questions that we can. If your question doesn't get answered, don't hesitate to email it at questions@luxresearchinc.com and we will respond. If at any point you experience technical difficulties such as a frozen screen, simply refresh your browser and check that your internet connection is strong. Now let's jump over to the presentation and I'll hand it over to Kristen.
Great, thanks, Tiffany. All right, so there's a common saying, the sky's the limit. It means that anything is possible. And as innovators, we tend to like this line of thinking. But when it comes to industrial innovation, we know that this statement is not true. The sky is not the limit. But I'm here today to argue that the material is, and few stories capture this better than one that quite literally takes us into the sky. So for most of aviation's history, aluminum has been king. Light, strong, easy to work with. It's one of the major backbones of the aerospace industry. But as engineers push for lighter and more fuel-efficient planes, aluminum has started to show its limits. Make it lighter, and you lose fracture toughness. Make it stronger, and you lose fatigue resistance. It's the classic engineering dilemma. Every improvement comes with a trade-off. And in aviation, we've reached the limit of what aluminum could give us. And then came a breakthrough. Carbon fiber changed everything. It offers the strength of aluminum, but the lightness of plastic. And with a specific strength more than 3 times that of aerospace aluminum, it redefined what was possible in aircraft design. And when Boeing introduced the 787 Dreamliner, more than half of its structure was made from carbon fiber composites. The result? A roughly 20% structural weight reduction and improvement in fuel efficiency. Not from a new engine, not from new aerodynamics, but from a new material. And behind that leap was Toray. What's significant here isn't just the Dreamliner itself. It's the business that Toray built around its carbon fibers over the years. Carbon fiber is no longer just an aerospace material. Today, it's found in everything from wind turbine blades to electric vehicles to even bicycles and tennis rackets. Once the material proved itself in the skies, Toray leveraged that credibility to expand across industries, from wind to automotive to consumer goods. But it's important to remember that carbon fiber didn't see success overnight. Adoption was much more gradual. Despite the performance data being there and the science being sound, adoption has taken decades. Why is this? Well, because an ecosystem needs to be established and the right market conditions met. For the Dreamliner, it took new composite manufacturing methods, plus advances in aircraft design and rising fuel costs, all aligning at the right moment for the material to take flight. So it wasn't just a single eureka moment. It was serendipity meeting timing and vision. And that brings us to today. Across industries, we're hitting the limits of what today's materials can deliver. The question isn't if there's another carbon fiber out there. The question is which materials and which moment will unlock the next industrial leap forward. And this is what we're going to explore for the rest of the presentation today. First, we're going to examine where today's materials are reaching their performance limits. Then we're going to highlight 5 groupings of materials that Lux believes will reshape industry. And finally, the barriers and timing factors that determine when great materials truly take off. So let's start with the present to understand where today's materials are running up against their limits. Take semiconductors, for example. Every year, our devices get faster, smaller, and more powerful thanks to a relentless race to pack more transistors onto silicon chips. Modern chips contain tens of billions of them. And over the past 2 decades, the power packed onto each square millimeter of silicon has increased more than 30-fold. Yet clock speeds, the measure of how fast a processor runs, have barely improved. So with each new generation of chip, we may be able to squeeze more performance from the same material, but at the cost of orders of magnitude more R&D, time, and energy. So these are the unmistakable signs of diminishing returns, the point where silicon itself has run out of room to grow. And like semiconductors, every major sector is running into its own material walls. Let's take a look at a few other examples. In infrastructure, corrosion and fatigue eat away at assets faster than we can maintain them. It's been estimated that global corrosion losses alone account for 3 to 4% of each nation's GDP every year. In water and environmental systems, as we push membranes or absorbents to be more selective, we lose processing efficiency. In wearable and flexible electronics, to make devices that bend, stretch, or integrate with the skin, we rely on polymer substrates or organic conductors, but flexibility often means sacrificing conductivity, stability, or lifetime. And lastly, in aerospace and mobility, even our best alloys and ceramics can't withstand the thermal cycling of hypersonic flight or the lightweighting needed for next-generation vehicles. So different markets, different problems, but the same underlying story. We're hitting material limits. Each sector is wrestling with its own version of a material trade-off that we can't seem to escape. But even beyond trade-offs, there's another layer of limitation with today's materials. It's not just what today's materials struggle to balance, it's what they can do at all. Across every sector, there are functionalities that don't yet exist in any commercially viable form. We lack materials that can monitor or heal themselves, that regulate heat or shape themselves in real time. These aren't just incremental improvements, they're entirely new material capabilities. So now that we've taken a look at the drawbacks of today's materials, the next question is, what are the next generation materials that have the potential to overcome and redefine industry limits? This is what we set out to understand. So how do we go about doing this? Well, we took a structured, data-driven approach. First, we wanted to cast a really wide net. We began with a broad scan of the materials landscape, analyzing thousands of research publications, patents, and startup activities. We wanted to capture early-stage signals of technical progress and commercialization intent. After cleaning up our initial list, we came up with just under 200 materials for further screening. From there, we screened each candidate against 3 key dimensions. Novelty to market. We asked how new a material family truly is, both in terms of its baseline maturity, but also credible next generation variations that point to new functionality. Performance potential. We looked for materials that could deliver clear step changes rather than incremental gains. We also looked at materials with entirely new functionalities. And then application breadth. We assessed how widely a material's properties could translate across sectors. We wanted to identify platform materials that demonstrate relevance in more than one domain. For example, carbon fibers, and how they evolve from aerospace into wind, automotive, sports equipment, and more. So by scoring and comparing our list of just under 200 materials through these 3 lenses, we identified several that consistently performed well across all criteria. Then taking this short list and grouping the materials on the list, we arrived at a set of 5 broader groupings. Together, these groupings represent distinct but complementary directions for future industrial materials development and define some of Lux's future materials coverage. These groupings include structural performance materials, porous framework materials, 2-dimensional materials, novel electronic materials, and photonic materials. So for each of these groupings, I'm next going to provide examples of specific materials, discuss key performance attributes and application potential, and I'll also share an example of some innovation in action, highlighting how progress is being made in their development today. So we'll begin where industrial materials innovation has always started, with structural performance. These are the load-bearing, heat-handling, impact-resisting backbone of industry. And for decades, structural materials have lived within familiar trade-offs in performance. But new structural materials are changing that equation. These are metals and ceramics engineered to deliver extreme combinations of mechanical strength, temperature stability, and lightweight performance. Examples of materials that came up in our screening include things like high entropy alloys that can achieve extraordinary strength, ductility, and thermal stability. Ultra high temperature ceramics that can endure beyond 2000 degrees Celsius, and ultralight metal foams and architectured lattices that flip the density strength trade-off. And if you can imagine, the application potential for these materials is enormous. But some of the most demanding and impactful applications include things like aerospace and hypersonic flight, where vehicles face temperatures exceeding 1500 degrees Celsius, extreme aerodynamic pressures, and rapid thermal cycling during acceleration and reentry. Other applications include electric vehicles, where lightweighting is paramount, and power generation, like nuclear, where extreme environments are experienced. So what I'm going to do is I'm going to turn next to place a spotlight on one of the material categories that scored highly in our screening, and this is high entropy alloys. So unlike conventional alloys, instead of optimizing one or two main elements, they blend 5 or more in near equal amounts, which opens an enormous compositional design space where there's quite literally stability and disorder. The excitement here stems from high entropy alloys' ability to combine strength, ductility, and thermal stability, which are properties that normally trade off. And this is due to the lattice distortion that you see on the slide here and sluggish diffusion. So in the simplest terms, the atoms here are really happy where they are because of this mix of different atomic sizes and bonding that makes it energetically difficult for them to move. So taking a look at innovation activity, for those not familiar, this figure shows our Lux Tech Signal. It's a composite score of academic publications, patents, funding, and Lux's own data to show a technology's overall innovation momentum. And as you can see from the figure, these materials were discovered in the early 2000s, but innovation interest has really picked up over the last decade, where we've seen academic publications tripling since 2018. So here, given this large compositional design space, computer-guided discovery and improved fabrication have really been big contributors to this accelerated progress. And one project that I'd like to highlight comes from the Raytheon Technologies Research Center, where a team set out to develop a new class of high temperature materials to push turbine operating temperatures to 1300 degrees Celsius, so far beyond the limits of today's nickel superalloys. So the Raytheon team used machine learning to computationally guide alloy discovery. They also used additive manufacturing to rapidly fabricate and test samples in record time. And while the team arrived at really, several promising high entropy alloy candidates, they found room temperature ductility consistently fell below the target, which exposed some shortcomings in our current models and highlighted the need for more experimental data. But this project captures the importance of advancements in computation, design, and fabrication to be able to accelerate progress in next generation materials, especially where there's a large compositional design space. So next, we're going to turn from strength to selectivity, to materials that can separate and store with molecular precision. Porous framework materials are crystalline, network-structured solids of metal organic nodes connected by molecular linkers that create really tunable pores at the nanometer scale. So I'm sure most of you on the line are familiar with metal organic frameworks that really gained a lot of interest for their highly tunable chemistry and exceptionally high surface areas. I mean, I think to date, surface areas above 10,000 meters squared per gram have been reported. So like a baseball field in just 1 gram. But in addition to MOFs, more recently, covalent organic frameworks have been gaining attention. These are similar, but rely entirely on organic building blocks to create lighter, more flexible frameworks. And now we're also seeing growing interest in hydrogen-bonded organic frameworks, assembled through hydrogen bonding that introduce a level of dynamic responsibility behavior not possible in more rigid frameworks. And so some key applications here include things like gas storage, where there's enormous surface areas, where the enormous surface areas and tunable pores allow them to capture and store gases like hydrogen, methane, and CO2 with exceptional efficiency. But also because of that high surface area and tunability, they're being explored for water treatment, as well as more effective and selective catalysts. In fact, this year's Nobel Prize in Chemistry was awarded for the development of metal organic frameworks for their potential to impact a wide range of industries. And when it comes to innovation momentum and innovation interest, since their discovery in the late 1990s, MOFs have exploded into one of the most active areas of materials research. Publication volume has increased nearly tenfold over the past decade, and over 100,000 known structures have been documented by labs around the world. On the commercial side, companies like Numat Technologies are overcoming sensitivity and integration challenges and scaling production, applying MOFs to a wide range of applications. And funding is flowing. Numat recently raised around $40 million for its Series C. But one of the most significant examples of MOF commercialization to date is BASF's collaboration with Sponte Technologies, which is a Canadian carbon capture company. Together, they developed a proprietary MOF sorbent designed for CO2 capture from industrial flue gases. This collaboration enabled Sponte's filters to operate at higher efficiency and reduce the cost of carbon capture. And BASF developed and scaled a continuous manufacturing process, ensuring reproducibility at hundreds of tons per year. This is one of the few examples of large-scale production of MOFs to date. And this partnership has shown that porous framework materials like MOFs are no longer just scientific novelties, but starting to actually have industrial relevance and impact. Our next platform takes us to the thinnest frontier of material science, the world of atomically thin solids. So two-dimensional materials, or 2D materials, are just a few atoms thick, yet display extraordinary control over electronic, optical, and mechanical behavior. So everyone on the line today is likely familiar with graphene. This is the best known example of a 2D material. But other promising 2D materials have emerged recently, like transition metal dichalcogenides that have semiconducting properties. But you can also stack different 2D materials together to design engineered solids with really specific properties, and even stack layers with just slight rotational misalignment to produce entirely new quantum phases and highly tunable electronic properties as well. And so key application here include things like electronics, where bulk silicon reaches its limits. 2D materials offer a combination of flexibility and electronic tunability. Their atomic thinness provides real precise control over charge transport, opening the door to things like flexible circuits, transparent electrodes, and other device architectures that conventional materials can't easily support. So let's take a deeper look at transition metal dichalcogenides, or TMDs for short. Imagine them as ultra-thin sandwiches where you have one layer of transition metal atoms like molybdenum or tungsten pressed between two layers of chalcogen atoms like sulfur or selenium. So what makes TMDs so exciting is that unlike graphene, which has zero band gap in the pure form, many TMD monolayers exhibit sizable direct band gaps in the visible or near infrared range. So this makes them strong candidates for next generation transistors, LEDs, photodetectors, and even ultra-thin solar cells. And when it comes to innovation interest, the journey of TMDs really took off after 2010, when scientists showed that molybdenum disulfide could be made just one layer thick, so thin enough to see through, yet still act as a transistor. And in the decades since, we've seen huge progress where scientists are unlocking other features through stacking or doping with other atoms. And most importantly, for adoption, engineers are now figuring out how to grow large wafer scale TMD films using industrial techniques. And a great example here comes from Samsung's Advanced Institute of Technology, which recently demonstrated 200 millimeter wafer scale transistors built in commercial semiconductor fab. So their work was published last year in Nature Electronics. And it shows us that the gap between the lab and the fab is closing, which is taking us closer to TMD's commercial applicability. Next, we move into a frontier where materials exploit new electronic and quantum degrees of freedom, like spin, topology, and correlated electron behavior. One of the 5 clusters that we identified, this is actually the broadest cluster, which contains several distinct materials that offer distinct functionalities and benefits. So it's a very broad cluster. But some of the materials that scored highly in our screening include things like topological materials, which exhibit this unusual quantum behavior where they conduct along their surfaces while remaining insulating in the bulk. Multiferroics, which couple material states like electric and magnetic properties, allowing them to be manipulated simultaneously. And neuromorphic materials, which mimic aspects of the brain by adapting, learning, and changing their response based on past stimuli. And so given the broad nature of this cluster, in terms of applications, the application space is broad as well, but includes things like computing, where materials can think and learn like the brain or process information using quantum effects, can promise leaps in speed and energy efficiency. Other applications include sensing, where quantum materials can detect the tiniest changes in fields or motion. And lastly, in connectivity devices, where multiferroic materials could enable ultra low power ways to convert, store, and transmit information. But we're going to shine the spotlight on topological materials as one of the interesting materials that came up in our research. These act like insulators on the inside, but let electricity flow easily along their surfaces. So in the simplest terms, the material's surface pathways are topologically protected, meaning they're really hard to disrupt, even if the material isn't perfect. And because these surface states carry charge with minimal loss that are hard to disrupt, they offer a foundation for devices that can deliver greater performance while using far less energy. And the theoretical ideas behind these topological phases of matter were recognized with the 2016 Nobel Prize in Physics. In terms of innovation activity, the story really took off here after 2010, when experiments on materials like bismuth selenide clearly demonstrated the predicted topological surface states for the first time. Before that, most studies were just theoretical and very mathematical in nature. And since this time, advances in imaging techniques, higher quality crystal growth methods, and powerful computational modeling have really pushed the field forward. So most of the innovation still comes from university and government labs, but momentum keeps building. And there are early signs of commercialization starting to appear. One example here is a Japanese startup called Topologic, which spun out of the University of Tokyo in 2021. The company is actually attempting to turn these exotic materials into real devices, starting with 2 promising areas: thermal sensors that can rapidly detect changes in heat flux, and low power memory that stores data without losing energy as heat. So in 2024, Topologic raised about $4.5 million to build prototypes. And it's still very early stages for the company. They're proving consistency and stability in their materials. But it's a sign that topological materials are beginning to move more from theory towards actual application, which is exciting. And then finally, onto our last material grouping. So photonic materials. These are materials engineered to shape, guide, and manipulate light, heat, and other electromagnetic waves with unprecedented precision. These materials include things like metamaterials and metasurfaces that steer light in ways that nature never could, radiative cooling and thermal photonic coatings that control heat flow for energy efficiency, and molecular photoswitches that enable dynamic light-triggered control of material properties. So key applications here include things like optics, where next-generation photonic materials are beginning to replace glass lens stacks with flat engineered surfaces. The impact could be cameras, displays, and optical devices becoming thinner, faster, and even smarter. Of interest are sensing and energy management. But for our final deep look today, we're going to look at optical metamaterials and metasurfaces. So instead of relying on what a material is made of, they rely on how it's built, with nanoscale patterns smaller than the wavelength of light. So by arranging these precise patterns, we can make light do things that nature never could. We can make it bend backwards, vanish, or focus through a flat surface instead of a curved lens. So the field here really took off in the early 2000s when scientists built the first metamaterials that made light bend in reverse, a phenomenon called negative refraction. But metasurfaces came after, and these brought ultra-thin, flat versions with the same effects, but using much simpler manufacturing. And today's research spans everything from manipulating radio waves to visible light, and is powered by better nanofabrication and modeling. But innovation activity is not just at academic stage anymore. We're starting to see startups and companies turning these concepts into real products. And a recent collaboration that I want to highlight is between Meta Reality Labs and Stanford University that unveiled an ultra-thin display for next-generation augmented reality devices. So by pairing metasurfaces with a programmable light modulator, the team could steer and shape light in real time without any moving parts. So in other words, they replaced bulky lenses and mirrors with a flat, software-controlled optical layer. So this example really brings us back to the limits of today's materials and shows us how next-generation materials are overcoming them to drive performance forward. Okay, so clearly a lot of exciting things are happening in the world of fundamental material science. But taking a step back, if these 5 material groups represent the future of performance, what stands between their potential and their adoption? So last, we're going to touch briefly on barriers for adoption and timing considerations. As we all know, new material adoption doesn't happen overnight. In fact, every breakthrough material faces a similar set of challenges that determine whether it remains a lab curiosity or becomes the next carbon fiber. In general, there are 4 barriers that stall progress. These are proof versus performance. So demonstrating performance in controlled environments is easy, but proving it under real-world conditions takes years. Manufacturing maturity, so even with strong lab data, scalable and cost-efficient production often lags by a decade or more. Ecosystem inertia, new materials rarely win alone. They need compatible design tools, processing equipment, and regulatory frameworks to see successful adoption. And lastly, value chain alignment. End users often won't invest until suppliers can guarantee availability, and suppliers won't scale until there's demand. So it's this classic chicken and the egg dilemma. But together, these barriers create a valley of disbelief between discovery and deployment. So as we saw in the carbon fiber example, adoption really accelerated when performance, ecosystem readiness, and market pressures all intersected. It wasn't just a better material, it was the right material at the right moment. But how do you apologies. But how do you identify that right moment? So by taking a step back, we can think about the ecosystem and market enablers for the 5 groupings of materials we discussed today. Each is moving along its own trajectory. So take porous framework, for example. In the near term, the adoption of MOFs are being enabled by improved production processes and integration, but we've also seen an uptick in industrial interest coming from their use in carbon capture and water treatment. So for MOFs, the moment is looking a lot closer. However, for some of the other materials, the moment seems much further away. There are still major technical barriers to overcome, and the market pull is not quite there. But that doesn't mean it will never be. So these are the important considerations beyond performance potential to take a look at and evaluate to understand the timing of material adoption. And at Lux, we've recently begun covering additional macro pressures, reshaping when and how materials scale. Some of these include things like material scarcity, where critical elements like nickel, cobalt, and rare earths are increasingly constrained, driving demand for substitutes and circularity, as well as evolving consumer expectations. We've been looking a lot at how consumers' expectations are evolving, and consumers are increasingly expecting more in terms of what their products and devices can do. And this is creating an opportunity for future materials to disrupt. So these macro pressures are creating pull conditions. So these are external incentives that are turning new materials from nice to haves to legitimate business opportunities. So some final takeaways here. One, I hope I've convinced you today that we've optimized today's materials to their limits. So across industries, incremental gains now come with exponentially higher costs, signaling the physical and functional boundaries of existing materials. 2, the next industrial leap will be materials-led. The 5 material clusters that I discussed today, so structural, porous, 2D, quantum electronic, and photonic, represent distinct yet complementary pathways that could break long-standing performance trade-offs and redefine what's possible in industry. And last, breakthroughs succeed when performance meets market timing and ecosystem readiness. When we talk about the next platform material, we're not just looking for the right chemistry, we're looking for the right convergence, because every material revolution begins when performance, ecosystem alignment, and market needs meet. And so some final takeaways to consider. It's really important to start today by identifying material limits in the industries you serve, engage with emerging platforms early, identify where core capabilities align with remaining technology challenges, and build an ecosystem lens, because the next platform material is not going to emerge in isolation. And with that, I'd like to thank you for tuning in to today's presentation, and I will take any questions from the audience.
Thanks, Kristen. As she mentioned, we'll be taking questions that you might have on the presentation. So you can go ahead and type any questions you have in the questions box below. If we don't get to your question, just a reminder that someone from Lex will be in touch. And as we wait for questions, maybe I can ask one. And going back to the very beginning where you mentioned which one of these materials is going to be the next carbon fiber, let's ask that. So which one of the 5 material groups that you mentioned is most likely to break through first? And what industry do you think that might be in?
Yeah, absolutely. I think of the materials that we discussed today, I think porous framework materials, especially MOFs, are likely the closest to meaningful commercial traction. Of course, there's still hurdles around their stability, manufacturability, turning powders into usable forms. But we are starting, like in the BASF example, seeing multi-ton scale production and early deployments in things like carbon capture, gas separation, water treatment. So these are areas where there's a real need for material innovation. So I'd probably say, or would start with porous framework materials. But I'd also keep an eye on things like optical metasurfaces. So companies like MetaLens, for example, there are already commercializing meta optics for things like sensing modules. And we're definitely seeing growing interest there and applying metasurfaces for next generation AR and VR systems. So yeah, I would think those two would have the nearest potential for adoption.
Yeah, I definitely see a lot of growth in both areas, especially my work in coatings. We have a question here on the intersection of these materials and AI. So, how do you see AI-driven materials discovery changing the timeline for the commercial viability of next generation materials? So, what's that intersection like?
Yeah, that's a great question. I think despite remaining challenges with AI in materials development, like data quality and availability, we're already starting to see it accelerate the front end of materials discovery. So there's a growing number of examples that I've come across where design cycles are being compressed from years to months. And I think this could especially be impactful for materials with those very large compositional spaces like high entropy alloys and metal organic frameworks. But I think it's also important to keep in mind that AI doesn't really eliminate a lot of the real world bottlenecks that I mentioned. So you still need scalable manufacturing, you still need to validate performance under operating conditions, and an ecosystem that can adopt the new material. So where AI could shift the curve by maybe making discovery faster and possibly smarter, it's not going to let us skip the curve, right? So commercialization timelines are still going to be governed by engineering and supply chain constraints. And of course, one thing that I keep hearing from clients is those rigorous review and certification processes that take a lot of time, right? So it's not going to let us skip over those.
Yeah, it is really exciting. I think we're all waiting for it, but definitely will take a while. We have another question here. So you highlighted 5 material areas today. You looked at a broader set. What are others that we should be looking at?
Oh yeah, that's a great question. And there were definitely other emerging materials that surfaced in our screening that didn't make it into the 5 clusters, but still